Thank you very much. Yeah, my name is Benjamin Werner. I'm from the University of Rostock. My supervisor is Professor Zander, and the title of my presentation is Experimental and Numerical Investigation of Fracture in Finite Wells by Cross-joint Specimens. In my introduction, I want to explain the necessity to investigate the fracture in well joints. After that, I want to show the specimens I used to investigate fracture in well joints. Then I show some hardness measurements and true stress-strain relationships. Then I want to explain finite element models I used, and then compare experimental and numerical results for force displacement curves. And then I show some results from collision analysis of the tank ship. And at the end, I want to conclude my presentation. Here you can see a collision accident that happened in Germany, in a harbor in Germany, a couple of years ago. On the left-hand side, the Niels-Holgersson ferry, or both are ferries, penetrating the wood. The other ship, damage at the Niels-Holgersson were just some plastic deformations, some minor plastic deformations. But here you can see the wood is damaged way worse. The outer shell is penetrated here, up here, and through the bulbous bow of the Niels-Holgersson at the waterline too. And because such accidents happen over and over again in frequently used water streets, it is necessary to ensure the structural integrity of the damaged ship, and one way to do that is with alternative stiffening system to increase the energy absorbing capability of the double hull structure. I investigated an alternative stiffening system that is called PVPS, that is a German abbreviation or acronym of plate strengthening stiffeners. You see here the outer shell with bulb profiles. That is a typical design, and on top of these bulb profiles, the PVPS are welded onto these bulb profiles, and as I just mentioned, they are welded onto them, and it's important in a collision scenario that these weld joints remain intact or keep their load capacity so that the double hull structure actually absorbs more energy than the typical design of a W structure. I want to show the specimens I used for different ones, K1 to K4. K1 and K2 are loaded with tensile forces in different directions to the well joints. The well joints are here in orange, and K3 and K4 are loaded with a constant moment. All 4 specimens are loaded until fracture. Some hardness measurements here on the left-hand side. You can see the weld joint taken from one specimen, the weld metal in the middle, and it's surrounded by the heat affected zone and the 2 plates here, the base material, and also the imprints of the hardness measurements. And here in the base material, there is a hardness of around 160, in the heat affected zone around or 330, and here in the weld metal, it's around 250 or 260. And 2 additional hardness measurements here along path 1 and path 2 are performed, and the results are here on the right hand side. The direction is here from the base material to the weld metal, and you can clearly see the maximum here as well in the heat affected zone with 330 in the green curve and 360 in the red curve. And from these hardness measurements, true stress strain curves are determined for the weld metal and the heat affected zone. The heat affected zone has a yield stress around 900 megapascal. The weld metal has a yield stress of 530 megapascal. And in addition, you can also see the true stress strain curve of the base material, which is determined by tensile tension tests. The finite element models, all 4 of them, K1 and K2, I used symmetry in all 3 directions, and for K3 and K4, symmetry in 2 directions. And these are here the bearing of the landing fixture. Those are rigid bodies, discretized with shell elements and everything else are solid elements. The discretization of the well joint is determined from this macro section on the left-hand side, and you can see here the weld metal surrounded by the heat affected zoom. The different material behavior, the true stress strain curves I just showed, are applied to both different areas, and an element size of around 0.5 millimeter is used to discretize the well joint and also the plates near the well joint. Also, a failure criterion is used to reproduce the fracture or failure in the well joint. I used the Rice and Tracy criterion. It's a function of the plastic strain here, depending on the stress triaxility. The stress triaxility is calculated from the hydrostatic stress state and von Mises equivalent stress. And you can see here the curve of the failure criterion. It's calibrated by the value epsilon critical. This is the failure strain at T equal 1/3. Uniaxial tension, and it is implemented in finite element software by a damage integral. Now I want to compare some experimental and numerical results, and I'm going to show you results from K4 under 4 point under a constant moment. You can see in red, green, and blue the force displacement curves of the experiment, and black the finite element analysis using the Rice and Tracy failure criterion. And here the force displacement curve is well reproduced up to 3.5 or 3.8 millimeter displacement, and fracture occurs here at 4.2 millimeters in the experiment at 5 or 5.2 or 3 millimeters. Here you can see the crack initiation in the white metal here highlighted with white elements. The yellow plate is the center plate of the specimen here. That's what you see here. And also the heat affected zoom. And yeah, as I said, the location of crack initiation is here in the weld metal at the welding gap, and the crack growth with an increasing load goes from that side of the weld joint along the welding gap this way to the other end, and also crosswise through the welding metal. And here I plotted the plastic strain as a function of the stress triaxility of the first element, which gets deleted here, the location of crack initiation, and also the function of the Rice-Tracy failure criterion. You see that the stress triaxility here is at failure at 2.1 or 2, and the plastic strain is around 5%. And I did that for all 4 different specimens, or the finite element analysis of all 4 experiments. Those are the path of the location of crack initiation of all 4. And now I want to show you some results of the collision analysis of a tanker or a tank ship. You can see here, it's just one section of the tank ship. The different colors have different element sizes, and the area of interest here is the orange one. It's discretized with 25 millimeter element size, and the striking ship here, that is it's a rigid body which is penetrating the double hull structure. Here, that is the cross-section of the finite element model I just showed, and here the orange area, you can see the inside of the outer shell, the frames and the stringer decks in green, and also the bulk profiles and the PVPS on top of them. To investigate the load capacity of these well joint between bulk profile and PVPS, I discretized here that area with solid elements relatively fine. You can see here the solid elements of the PVPS, the well joint, and the bulk of the bulk profiles, and I applied the calibrated Rice and Tracy failure criterion to these well joints. And I just want to exemplarily show 2 force displacement curves of 2 different collision analyses of the tank ship. One without PVPS, the typical double hull design, and one with PVPS, integrating these force displacement curves into the energy, and by doing that, or from these energy displacement curves, an increase of 20% can be determined. 20% increase of the doubler structure by the PVPS. And with that, I want to conclude my presentation. First, it was possible to determine true stress relationships from hardness measurements, applying these true stress-strain relationships of the heat affected zone of the weld metal to the finite element model of the cross-strength specimen. It was possible to reproduce the experimental force displacement curves of the cross-strength specimens. Furthermore, it was possible to calibrate the Rice and Tracy failure criterion, and applying the calibrated Rice and Tracy failure criterion to the finite element model of the tank ship, it was possible to investigate the load capacity of the weld joints between PVPS and bottom profile. Thank you for your attention.